Hi again, it's time for another Physics 142 video. And in this video, I want to continue our discussion of inductors. So we've talked about the inductors. They're the circuit elements that resist change in your circuit, right? Their whole goal is to keep your circuit running with a steady current. If you try to change the current, they're going to resist that change. So if you try to increase the current, it's going to act like a resistor, try to fight back, right? If you try to decrease the current, it will act like a power supply. It'll try to give you more current, right? So that's what inductors do. Now, in this video, I want to think a little bit about how inductors, these wire loops with some current or with some inductance L, how to combine them with resistors. What happens if you have a circuit that has not just an inductor in it, but an inductor and a resistor? How do we think about them sort of in combination? And to do that, I first want to sort of do a little bit of review. I want to bring you back to a circuit that we looked at earlier this semester. This is a circuit that had a capacitor and a resistor in it. All right, how do we deal with circuits when we had capacitors and resistors in it together? So let's see if we can remember how that worked a little bit. Right, so you might remember that with these RC circuits, what we ended up doing is we said, well, what happens if, just after we close this switch, what would happen if we sort of thought about like a Kirchhoff's loop rule, right? If we sort of started at a spot and we walked around our circuit and we thought about how the potential changed at each spot, we realized, well, if we go up the power supply, then we gain some potential. Right? When we cross the resistor, we lose some potential. We lose IR's worth of potential. And we also, then the capacitor also takes away some potential. So we lost Q over C, I think, is the potential across a capacitor, right? It's storing energy there, and we realized that equals 0. And a cool thing that we were able to do is we said, well, I, that's just change in Q, right? So we could write this as V minus dq dt times r, right? Minus q over c. And we realized then that this was a differential equation, and we didn't actually solve the differential equation. We're going to leave that until you actually take diffie-q, right? But what we realized is that, well, this equation says that if we have q, the function q in it, and we have the derivative of q, the only sorts of things that would work if this is true, all right, the only things where the amount of q is related to the rate of change of q has to be exponentials, right? That when you have some function, if you take the derivative, you sort of need to get something similar back so that these things can equal each other. And so the way you do that is with exponential functions. And so we ended up realizing that we could write down the amount of charge on the capacitor, right? Q on the capacitor as a function of time ended up being C times V times 1 minus e to the minus t over RC. Right? So it ended up having this cool exponential in it. And basically what that looked like when we made a graph of it, right? Let's remember if we can remember what that graph looked like. Actually, let me, for space reasons, I'm going to put the graph over here. Right? So we'll put the graph over here. And we've got time versus charge, right? Is basically what this says is if you're at time equals 0, right? Time equals 0, you have e to the 0, right? And e to the 0 is 1, so 1 minus 1, that means you have no charge, right? But then over time, right, eventually you'll get up to the point where you'll have e to the minus a very big number, right, which is basically 0. So then you have 1 minus 0, and basically this just becomes CV, right? So you end up getting up to the total charge of CV, but it sort of takes some time, right? You sort of have this growth. All right, and the charge in the capacitor, it starts at none, and over time it grows to basically be up to its full amount. And it's this exponential kind of growth here. And we realized that this RC, we called that the capacitive time constant, right? Remember that? And basically, it was just sort of a convenient way that told us at time equals RC that you've charged it up about 63%. right? In every RC that you go on, you charge 63% more of where you were, right? So, so this is all a little bit review. Maybe this brings some things back, will be helpful on the final exam. There's one other thing I wanted to point out about these RC circuits, right? We know this, right? We remember that just after the switch closed, basically this thing just acts like a wire, right? You've got a bunch of all the charges flow. And actually here, before I go there, I'm getting ahead of myself. If we talked about the current, we realize the current is the derivative of this function, right? If this is the charge on the capacitor, we could also think about the current flowing through the capacitor, and that ended up being equal to V over R times E to the minus T over RC, right? When you take the derivative of this term goes away, you get a factor of RC that comes down in front, the C's cancel, and you just have V over R. All right, and so that plot, right, the plot of current over time, and I guess maybe I should have left a little more space, but the current over time plot, right, if we make that plot, then what you end up getting is this exponential decay, right? At time equals 0, you're at a maximum, and then the current decays with time. And so that, we sort of thought about that. We said capacitors at early times are like wires. All the current is flowing through them. And after a long time, they're like acting like infinite resistors. No current flows through them after a long time, right? So, and this was the math that sort of got us there. All right, so that's RC circuits, kind of old news, right? That was capacitors and, fun stuff that will show up on the exam. But, so what we're interested in now, though, is what about circuits that have inductors in them, right? How are those the same or different? How can we treat those? Well, let's perform a similar analysis here, all right? Let's go ahead and apply Kirchhoff's loop rule here, right? We start at some potential, right? And then we're going to go around. So you gain a potential V, and then we lose I times R. And then, well, what's the potential change across an inductor, right? What's the potential change across an inductor? Well, you might remember, let's just jot down the formula, that the potential across an inductor is minus L di dt, where the minus sign says we're opposing the change. So if I just close the switch, I'm getting positive, an increase in current. So I definitely want to keep the minus sign. So we'll go minus L di dt, right? That will, lose potential going across it if the current is increasing, all right? And so that's going to be equal to 0. And I'd like to point something out to you here, that this equation, this is again a differential equation, right? It has the amount of current I in it and the rate of change in the current, right? So it has a derivative and the function in it. So again, the solution must be some sort of exponential, right? Something that when you take the derivative, you get the function back again. And, if we compare this equation, it actually looks really similar to this charge equation, right? These have a lot of similarities, right? dq dt is like di dt, except instead of an R, I have an L, right? And instead of Q here, I have I. So, this is an equation in I, not in Q, right? This one has Q's, this one has I's. This one has an L instead of an R. And instead, this 1 over C and R are kind of the same, right? R here is the same as 1 over C. So if you end up solving this, all right, it basically is the same differential equations math. You just have different constants in it, all right? And so what you end up getting is an I of t function, a current as a function of time, that looks a lot like this charge as a function of time equation from the RC circuit. So let's write that down and see if we can compare them. All right, if you do the differential equations math, what you end up getting is that I as a function of t is V over R times 1 minus E to the minus R over L times t. All right, so very similar, right? It's just that C got replaced with 1 over R, okay? And the V was still in the same place. The V was still in the same place, right? And here we have, again, C is getting replaced with 1 over R, right? And R is getting replaced with L. So a few different variables, but, similar-ish looking equation at the end. And so what does this mean, okay, if we make sort of a plot of this, right? Let's make a plot of current versus time here for the inductor. Well, it's going to look a lot like this plot, right? At time equals 0, then we have basically no current, right? Time equals 0, we have 1 minus e to the 0, that's 1 minus 1, that's basically no current. But as time goes on, this number gets smaller and smaller and smaller, and eventually you get up to a current of V over R, which makes a lot of sense, right? V equals IR, that's Ohm's law, right? So that's the current that we should get up to. And this is sort of that idea that we were talking about the other day about this back EMF, right? That having this inductor, right, it's basically delaying how your current gets turned on. So rather than when you shut the switch, the current just going instantly on, right? There's this sort of exponential growth. It takes some time to get there. And what I'd like to point out is let's compare this I versus T plot to this I versus T plot, right? You see for the capacitors, they start with lots of current, right? And then over time, they decrease to no current, right? So they start like wires and they end up like infinite resistors. All right. Inductors work the opposite way. They start with a lot of resistance. They're really pushing back against that change. But in the end, once the current's up and flowing, they're like, it's fine. This is the way things are. Let's keep it hunky-dory. And, they basically act as wires after a long period of time, right? After a long time, then it's just V over R here. Okay. So in a way, they're sort of opposites. So I should, we'll mark that down. Now I should mention, right here, we defined this tau as RC, right? This time scale as RC. You can also define a tau for an inductor. So a tau for inductors. And here it's the tau for inductors, all right, is going to be L over R. All right, so here it was RC, all right, 1 over RC. Here we have 1 over L over R, right? So another way of rewriting this equation would be I of t is V over R times 1 minus e to the minus t over tau L, all right? And that would be very similar to writing this with minus t over tau C, right? So very similar equation, except this one's a current equation, this one's a charge equation, right? The current equations actually work exactly opposite to each other. So, this tau L, again, it's when you get charged up to 63%, when your current flow is up to about 63%, right? So after tau L, which is L over R, that's when you're going to have 63% of your current flow. So I think it's pretty cool. The math is kind of similar, but the end result is actually basically the exact opposite, that you end up with these capacitors and inductors acting sort of as opposites. All right, so I think that it would be good for us to sort of do a quick application example of this. All right, so let's move the board down a little bit and see if we can just think about this in just a little bit more detail. All right, so we'll get just a little bit more space here. Okay, that should do. All right, so I'm going to draw two circuits here. All right, so first I will draw a circuit that has a capacitor in it. So we'll go over here and let's have some power supply, gives us a potential V. All right, and then we've got a resistor, R1, and let's put a capacitor in it like before. All right, and we'll put a little switch in it like before. But now I also want to put a resistor in parallel with that capacitor, R2. All right, so you might have seen something like this on a previous exam, right? And maybe you know where I'm going with it. All right, so this is sort of circuit number 1. It's got a capacitor in it and a couple of resistors. And now let's draw another circuit over here. All right, and we're going to draw basically the same circuit. right? Basically the same circuit, except you can probably anticipate what change I'm going to make, right? So here again, I'll have resistor R1, but now I'm going to put an inductor here, right? So we'll put an inductor in. There we go. Nice inductor. There's my switch. And of course, the inductor now will have that be in parallel with a resistor as well. Okay? And the question I want to ask is, like what happens, first of all, right after I close the switch, or immediately after I close the switch, what's going to happen, right? That's what I want to know. Immediately after I close the switch, right? So right after. And then later I want to know about a long time, right? So long time later, right? A long time later. What happens, all right? So let's see if we can compare and contrast here what happens with these two circuits. So these RC circuits, you've analyzed them before. Some of you got it right on the exam, right? So right after you close the switch, capacitors act like wires, right? Capacitors act like wires. They have essentially no resistance, right? All the current wants to flow through them. And so if all the current is flowing through the capacitor, that means basically none of the current is flowing over here, right? Basically no current over there on the right. And so this is just basically a circuit that sort of has V and R1, and that's it, right? That's the R2 is basically getting ignored. And so if we want to know the current, I is just going to be V over R1, right? Another way to think about that, right, is if we think about the equivalent capacitance of these two, right? Maybe I'll call that 1 over R equivalent of, well, let's call it RC2, right? The equivalent resistance of the capacitor and the resistor, right? Well, that would be like 1 over, what's the, resistance initially? That would be 1 over 0. Well, what's that? Well, don't worry about it. We'll figure it out. All right, 1 over 0 plus 1 over R2. Well, 1 over 0, that's basically infinity, right? If you divide by 0, you get infinity. So this just comes out to be infinity. So 1 over the equivalent resistance is infinity. So I flip it over. I get that the equivalent resistance is 1 over infinity, which is 0, right? Divide by infinity is 0. So basically, there's no resistance here. All of it just flows through. So you're just left with R1 as the total resistance right afterwards. All right, now contrast that after a long time, right? After a long time, C is going to start acting like an infinite resistor, right? C starts acting like an infinite resistor. And, well, when C acts like an infinite resistor, basically then none of the current wants to flow here, right? So after a long time, nope, can't go through there, right? All the current has to go through there. So after a long time, I'll move this up just a little bit. After a long time, my circuit just looks sort of like this. Right, it's got R1, and then, can't go into the capacitor, so it's all got to go through R2, right? R1, it all goes through R2, and so then this is just a nice series circuit, right, with R1 and R2 in series. Those just add up, and so I is just going to be V over R1 plus R2. Right, so after a long time, and we'll just note, right, the C acts like infinite resistor. Okay. All right. Now let's review. All right. Hopefully it's some good review. All right. Fun and exciting review. What about the inductor here? All right. What's going on over here with the inductor? Well, and this maybe I didn't make this very clear. Right. This is my inductor L, and we've got a potential V across that. Right. My little squiggles, my circle squiggles for the inductor. Got to keep that clear from my jagged resistor, right? All right, well, right after I close the switch, there's a lot of change happening, right? We're trying to get things ramped up. There's a lot of change. The inductor doesn't like it, so the inductor is going to act like an infinite resistor. Right after I close the switch, it says, No current's going through here, all right? I don't like the change. I'm going to fight back against that change. And so if you're acting like an infinite resistor here, well, that's going to be sort of the long time case of the capacitor, right? Then nothing flows through here, and I just get this series circuit again with R1 and R2, and I get that I must be V over R1 plus R2, all right? Well, after a long time, can you see where we're going with this? After a long time, we've ramped things up. We've got just, all the currents flowing. And so there's no changes happening basically after a long time, right? After a long time, there's very little change. And if there's very little change, inductors are happy with that. Then they're not going to fight back. They're just going to act like wires. So then the inductors will act like wires. All right. And so then my circuit just looks like, this sort of thing where I have R1 and, a wire, right? And nothing's going to go, I can have this other resistor, but if I've got a wire, nothing's going to flow through the resistance, right? Everything's going to take the easy path, right? We always take the easy path. And so here, we're just going to have I is V over R1. And so hopefully you can see this helps sort of contrast again, the inductor circuits with the capacitor circuits, right? And see really how they act like opposites, right? That the behavior of a capacitor right after you close the switch is very similar to the long time behavior of an inductor. And so, hopefully this raises a question to you. If we have basically these opposite devices, right? Capacitors and inductors, they sort of work in opposite ways. What happens if you stick them together? Well, stick around. We'll do that in the next video.